I said Mike Underhill probably needs no introduction to most of you because he's over the years he's given quite a few talks to our Sussex network. What you may not know is that Mike spent about 31 years in industry with companies such as Philips and Thorney MI. And then he moved into the University of Surrey. I think he spent 11 years there, but even when he finished with them, he still carried on giving part-time course lectures at Surrey. And I think he estimated that over 30-odd years, he must have taught and hopefully inspired over 1,300 students in the various fields. His courses were in things like radar, radio frequency, microwave, and antenna and propagation. So in that field, Mike has made quite a contribution to our future engineers. Okay, now, of course, we all take these things for granted. I know very little about them, to be honest, so I'm hoping tonight I'm going to learn a bit, and we all will. So Mike, thank you, over to you.
Right, thank you very much, David. Am I too loud? Yes, a little bit. Can you switch that off?
I'm trying to switch it off, but it's...
Okay.
No, that's it.
Right, okay. Right, well, I hope you'll get something out of this. It is a master's level course, so if you, and it is a little bit specialised, but I'm going to try and cover it very quickly in some areas and maybe dig a bit deeper in other areas. But I'll start off, as it said in the original blurb, which was in our website and so on. It's a tribute to an ex-colleague of mine, Ian Robertson, of Leeds University, who sadly died at the far too early age of 61 a month before. He was going to give 3 lectures. This is one of them, but with a little bit out of one of the other lectures. So, and you'll have to keep an eye on me because it was a 1.5 hour lecture. So I will have to go, I'm going to try and keep below an hour, right? And so I will have to go fairly fast or skip over various sections. Okay, so here we are. That's one of Ian's original introductory slides, and it was originally called Transceivers and Mobile Devices. So the focus is there, but when you get into the notes, you find it's not just the mobile devices, it's the systems which actually the devices have to operate in and they have to interact with, and the devices themselves are really sophisticated systems. A mobile phone, I'll get mine out just so I can wave it from time to time, and they really are sophisticated devices. So anyway, let's start off. This is Ian's original notes, what he covered, and I've put in a sort of orange colour are the ones which perhaps I'll spend a bit more time on. The other ones I will skip over and see what we can do. But and also I've put in something which I didn't put up here, up at the systems level, because there's some very interesting interactions with world economy, which is causing, you know, slowing up or speeding up or whatever the development, particularly when it comes to 6G, which we're going to talk about. So here's the handset evolution. You can see the sort of selection of handsets going from this original analog system. It was the kind of system was up in the sort of 800 megahertz band. It's the kind of system that the press used to get all these scurrilous stories out of Princess Diana and talking to someone. That was the kind of system that some of the intercepts, they was intercepting mobile phones, either of that one or that one. So that was the early analog system. It was open. You could. I had a little receiver, and I could listen to things there. I was a good boy, and I didn't do too much of it, and I certainly didn't try and get money out of the press for listening to it. So anyway, it's a big business. It really is a big business. 1.3. This is 2020, just 1 year, and 1.3 billion, and these are the players: Samsung, Apple, Huawei, Xiaomi, I don't know, Oppo and others. Those are the big players, and you can see the proportions that they, if you can read, the others were quite big there. It's changed now, but we'll see as we go along. But that was 2020, and on the chart that's 2020, and an interesting thing has happened to the numbers per year. They actually went down. So I don't know if it was COVID or whatever it was, they went down, and they've only just, they're creeping back up again. So 2020 was a low year, and then it crept up a bit and then went down. So there is a distinct flattening out. We are saturated with mobile phones pretty well on that. So that gives you some idea of the market. Then let's look at the systems evolution that we've got on that. What have they been used for? What systems use them and so on? TAX 1G up is, as I said, that's the analog system up there. 2G is the GSM, 900 megs, so that is an improvement in as much as that it was the first digital system. That was the 2G system. The digits mean it is possible to encrypt the calls so that you can't readily and easily be listened into. Quite low, tens of kilobits, that's all you could actually get on the data on that. So useless for getting into the internet. 3G, 2.2 gigahertz, so it's actually going up to a higher frequency band than before, and medium data rates, megabits, not kilobits, but megabits per second. That's obviously an improvement. We are now in the 4G area, which is so it's roughly 10 times better. It's internet protocol based. It uses some new spectrum. It swiped the analog TV bands when analog TV went all digital. All those that band was used. It is, we'll see in a minute, a very, very thirsty of spectrum activity indeed. So that's 4G, spectrum analog TV. Now 5G is a step into very much in terms of speed. It's, well, it says ultra fast, so that's tens of megabits, so gigabits is 100 times, that's tens of, so a gigabit is 1,000 times, but that was tens of, so this 5G is better than by a factor of 100 in terms of what you can do on that. So, and it uses new spectrum. This is really, well, we'll see a little map of the spectrum in a minute, but that gives you some idea of what it actually is used. It is beginning to be the internet, or the IoT, everything interconnected type of arrangement, gigabits per second. Well, what about 6G, sub-terahertz? So just so you know what sub-terahertz means, I'll put it up there, but it basically means 0.3 terahertz to 3 terahertz, which is 300 gigahertz to 3,000 gigahertz. So it really is a step, well, a couple of steps increase, and the bandwidth available there is very, very very good, and you can start having your smart cars and everything interconnected and so on in the 5G, which is shown in this picture. And 4G is okay, it's useful, it's a pretty useful system, but it's nowhere near what 5G does. And well, 6G, well, we'll talk about it a little bit later. Let's see about that in a moment. So here we have the cellular systems. Well, why do we have to use cellular systems? Well, each transmitter, base station, transmitter, receiver, has got a limited range. Okay, you can up the power, but actually that doesn't increase the range very much by comparison. If you're at lower frequencies, you get more range. So the old 1G and 2G systems had more range than 3G, 4G and 5G. And it is interesting that we're in the situation where the providers are closing down the 3G system in the countryside and leaving the 2G system to run for those of us who live in the countryside away from handy base stations. So in fact there's a safety alarm which we've got, which you can hang around your neck, my wife and I, and that has had to be removed, and we've had to be given a 4G one because the 3G system is already being closed down. It's already being closed down, but then if you're way out, then you will still use the 2G system for certain things. Anyway, back to this: why use a cellular system? For a reason, actually, mobile needs lower transmit power. So you need lots of base stations close to the mobile. It's not so difficult to transmit, but it's from the base station, but it is difficult to transmit from the mobile itself. So you can, with a cluster of base stations, you can support many more users. You can reuse the frequencies from one cell to another. You can use the same piece of bandwidth over and over again, depending on the spacing of things. But to do that, you need many base stations, and that costs quite a lot of money. So these are the kind of things you have. Here's the aerials, the antennas there on the top of the tower there. This is one. How many of you seen that one? A few of you, yes. That is, I'm always amused at that. There was one on the A3 which I used to pass, and they're still, I'm not sure how many of them are still around. I haven't looked that closely. But there's all the transmitters, receivers in that there, and the aerials, the antennas are at the top. And if you come from Guildford, next time you look at the cathedral, just remember, just below the angel on top of the Guildford Cathedral, there's a whole load of base station stuff pointing in different sectors in different ways. Quite a complicated setup of base stations. So next time you go, cast your eyes upwards, as they say. So anyway, here's a typical macro cell. That means one of these big cells we've just seen. Indoor model base station, and there's the various bits. The filter shelf, we'll talk about that. Amplifier shelf, baseband shelf, that means down at after everything's been demodulated from the high carrier frequencies down to sort of fiber frequencies, depending on you need a bit of bandwidth on the latest ones. And then the input-output panel and power and so on, that is on the Leeson BTS system. So here's you can see the sector antennas, which I mentioned around the top, and these dish antennas are used for microwave links to interconnect between the base stations or connect them up to the system. So when you look carefully, you'll often see them pointing in various directions, though they may be actually piggybacking a microwave link, receiving it there and transmitting it that way. So it's quite a complicated system which you have to deal with that. And then, of course, the sector antenna has a particular problem in that if a car or a mobile handset moves from one sector to another, you've got all the problem of switching to one sector to the other. You've got that problem as well as moving to a new base station. So it is a complicated system. It's all dynamic, but it's all hidden under, it's pretty good, I always think. Here is antennas. How many do we need? This is from Peter Song and David Barker, who I do not know, but anyway, that is the antenna patterns for us, that kind of antenna superimposed on some town or city that I do not know. So anyway, in addition to these macro cells, you need micro cells, particularly for 4G, and particularly for 5G, and they're hidden away. You won't notice them. This is Northumberland Avenue in London. There's McDonald's, and there's a little micro cell above the McDonald's sign. So that's the way. Keep your eyes open. You might be able to see them from time to time. Here's another one on in, I don't know which station, Euston Station or somewhere. There's one hidden away inside, because inside a large building you don't get a very good signal, but if it's a large building like that, you've got lots of people, so you've got to have some sort of micro cell inside there to do the trick. So mobile handset block diagram. This gives you some idea of the bits of the system and the fact that it is quite a complicated system. So if we start at the aerial, the antenna, here is the RF transceiver. Now that RF and digital are very different animals, so the technology which you use for one is not necessarily ideally suited to another. So over the last 20 years, I suppose, it's been a continual struggle to actually get them to be compatible in the same little handset and to actually use as far as possible the same integrated circuit technology for the two, or compatible. Silicon is still the preferred way of doing things. So you then have analog baseband processing. You translate down to a baseband, and then you have analog to digital converter and a digital to analog converter. Digital analog converter going that way, and analog digital converter here. So the digits go into the digital signal processing, DSP, and out. These are all two-way things like that, and then so that is done, all the filtering and separating of the channels and making sure that one channel doesn't interfere with another is all done there. And then you have at a much lower frequency, than these ones, then you will have an analog and digital analog to go to the microphone and speaker. These are audio frequencies, whereas these are at medium RF radio frequencies. But the processor has got a lot of things to control. It's got those things there. It also has got memory, a SIM card, touch screen, the buttons, and then the alerts, which may or may not be done on the ordinary speaker. They might be done by a separate thing, which is done on some of them. So now here is all that lot compressed into the layout of a chip. Now the battery goes in here. So a lot of the space, that gives you some idea of the space that you've got to leave for the battery for a typical system like that. Then you can identify by the colours the various bits of this. I'll run through them quickly. This is the Apple A11 Bionic 64-bit ARM-based silicon on SoC, I can't remember, designed by Apple, manufactured by TSMC. Now this is an interesting thing. There's the number of companies involved in making a mobile phone are far greater than you think. You think Apple did it. No, they did not. They actually had lots of subcontractors doing various bits. Okay, they stitched them together, but that is different. For example, okay, there's another Apple thing. Then the blue is the light blue is the Apple codec. That's codes from digital to analog, or does error correcting codes as well as part of it. There's the battery charger. So you've got to think of all these things. It's quite big because it's taking quite a lot of power. There aren't many active devices in it, but it's got to take up some area. There's the green is the USB charger. Interesting, it's separate thing, separate chip on that. What else is interesting? Power management IC. So power management is a really major job, all ticking away unbeknownst to anybody inside the mobile phone. What else we got? There's another power management IC on there. So it's really a very, very large system when you come, all hidden inside the phone itself, all hidden inside there. So this is a slightly more recent one, and much the same bits and pieces, different sizes and certainly different performance. Broadcom, different company. Broadcom power amplifier model, Skyworks power amplifiers, different company. Qualcomm Snapdragon LTE modem. LTE stands for long-term evolution. It's the first seriously good upgrade of the system, which transferred 3G to 4G essentially. So it's the it is so much faster. It gives you music and video really fast, far better than 3G. It was actually originally called 3G LTE, but it was actually a bridge to 4G on that. So that's the bits, and you can see the other bits and pieces on here. Different layout, except for, okay, the battery goes in there. So that gives you some idea of what it's like. Now let's turn to, are they getting better? Are they getting smaller? Are they getting more power efficient? Well, let's look at Moore's law. And Moore's law is plotted like here on a log scale on there and a linear scale on dates on here. And you can see what has happened. Well, what's the log scale of? It's nanometers. That's 1/1000th of a micrometer, or micron, 1/1000th of a micron. And you may wonder what these numbers mean. They actually are a measure of the size of one individual transistor. It's actually what they call the node of the transistor. They talk about, 60 nanometer node on that. We are now down below 10 and creeping down to 1, and some manufacturers are claiming better than 1. But in a way, I'll tell you why, it's all hype going down to as small as that. So just let's go back a bit. The original Moore's law only predicted for 10 years. So it actually was back in 1965, back here. So it finished at 10 years, predicted for 10 years. And it's gone on ever since 1975, and it's still pretty well going on now. And it's the increase in the number of transistors in a microchip. That's what, in fact, the measure of it is. Now, the microchip could get bigger in 2 dimensions, or it could get bigger also in 3 dimensions, and we'll see the technology has really advanced on that. Here is a stack, which is interconnect stacked for the Intel FinFET technology. Okay, these are stacks, if you like, that they've got transistors in each part of the stack. So you can actually go in terms of area on the chip, which was counted that. You're cheating, but it's a very nice cheat. You're going up to there. This is actually more to do, this one happens to be more to do with the transmit-receive side, the RF side on there, and this is the Intel RF CMOS transceiver. You can get some idea, and that is, if you like, been stacked up into a stack in that arrangement there. So let's turn over a little bit to microwave and millimeter wave ICs. This is, I filched out another part of Ian's notes. And right, so here we are. This continues on the story of what a nanometer means to a commercial guy. Not to a physics guy, not to an engineer, but it means to the guys who are expert in hype. So we are now node name, and this it shows you the way they've hyped it. 5 nanometers, 3 nanometers, 2, 1. But the actual gate pitch, which was where it was originally defined, stopped at just below 60, or almost stopped at 51 nanometers. So in fact, the gate pitch has actually barely changed. The metal pitch, that means the interconnections which go into it have improved, but only by a factor 2 over, 7 years. But then you've got stacking as well to take into account, and if you take into account performance as well, you can argue that to make that curve continue on. And so these commercial guys are talking about their 1.8 nanometer system and this technology, and even below that 0.9, etc. But it's all hype. It's nothing to do with the original definition, which was the gate pitch, which is the central part of a CMOS type transistor. So this, for example, is what you can do, though. This is 7 nanometer technology, 54 billion transistors there. 54 billion transistors. Launched in 2020. Okay, the size of the die, that means the actual chip that you chop out, is actually that many. It's quite big, 8.26 millimeters squared. But it's 2,000 gigabits dynamic memory, dynamic random access memory. That's the bandwidth. So that's 1 each. So that's actually roughly equivalent to that. So that gives you some idea of where things have reached on that. Now this is Moore's law, just quickly plotted in a different way. It should have been actually plotted in my mind on no, it's fair enough. This is a linear scale on this time of the number of transistors on a chip, on an individual one die, one dice, as some people prefer to call it. And this is what has happened. It's actually barely moved because of the scale used. That's 20,000. In the time when I was doing a little bit of chip design for frequency synthesizers, we were limited to 1 to 2,000 chips, transistors on a chip. So 1 to 2,000. So it really has crept up, and it suddenly took off around about 2010. And AI, artificial intelligence, is really pushing that right up into the stratosphere, shall we say. This is another plot of the thing. You can see the feature size. It's actually a plot of the charts I've already shown you, so I'll move on. So Intel CMOS transceiver for the 5 gigahertz band. So this is when we moved up to first from 2.5 or whatever it is to 5 gigahertz, then you needed a design for that. And I think internet connected stack so it's a stacked arrangement as well. Again, I think we've seen that one before. Just finally on this, semiconductor industry evolution. All this going to higher and higher density, more and more transistors, is coming at a great price. This is the technology. This is 2002, 2003. So I was operating in this region when I had to design roughly in this, well, 130 to there in this region. But it's actually gone down to now, and it's now 7 nanometers. But look what it's plotted against. This is the number of fabrication units that are capable of operating that technology. And when you get down below 5 to 3 nanometers, there are only 2 players. One is TSMC, which is in Taiwan, and the other one is Samsung, which is in South Korea. Everybody else is behind. The Russians, their fabs are still only in the 65 region. China is a bit better, but they're still not players. China makes the largest volume of chips, but it doesn't make them anywhere near to their technology. So this is a very politically dangerous situation. If China invades Taiwan and tries to shut down TSMC, then the whole of the electronics industry, or the high-end part of the electronics industry, is under severe threat. Now, if China does, very interesting thing, when I was doing this as a repeat lecture for the students, there was a Belgian guy, and he got his mobile phone out and he started doing it. Very rude, of course, people doing that when you're trying to talk. But he came up with a very interesting thing. On that, it said that if China invades TSMC, then TSMC has put in something so that China will be not able to make any chips. They can control what is made and what is not from outside the country. So it's a highly political situation. Very, very interesting. But it is a rather dangerous situation at the moment. And China, obviously, in the latest news, is circling their navy around Taiwan to make things threatening for them. But it was only 2. Now, the Americans are doing a catch-up. There are some fabs not shown on here, which are going to, in fact, try and do some catch-up on that. But it costs 15 to 20 billion pounds to make a modern fab. And it takes, I don't know, 5 to 6 years to actually build it and get it up. the thing about TSMC is they have really cracked the reliability issue greater than anybody else. Their chips are far more reliable, cleaner. They've got they've really done a good job. So we will be in a difficult position. So this is actually now going to the size of the wafer, which has all these things on which you dice up into individual dies. Number of semiconductor fabs using 300 nanometer wafers, and okay, that has gone up on there, but so there are ways around it. And then finally, where the new semiconductor, well, I've dealt with that. East Asia is really the place where TSMC and Samsung. So US is over here, and anyway, and I think ARM gets their chips, the ARM chips which we saw earlier, which will go into phones. They get their chips made by TSMC. So it's all interrelated. So supply risk management platform is fueled with robust, normalized, intelligent databases, etc., etc. They try very hard to keep it all flowing. Right, silicon technology. This is actually slight change of direction. It's what's happening about the technology, the various things. I'm going to move on fairly fast, but roughly, perhaps we'll just a thing called FinFET, which means you actually have a fin going up, and the transistor is made of fin, which it actually has two sides. So you can actually, the gate it's a two-sided thing, so it can flow across in a very compact way. And then I think there's some better pictures of FinFET later, but on that's probably in the road. Right, I'll move on. Intel process technology. I think. Oh, here's a FinFET. I'll go with these are the various ones of chatting, but they've gone to sort of thin fills and then a multi-bridge channel interconnect. There's lots of new technologies, and the very latest, which has not been put into production yet, is a all-round type arrangement, which is TSMC haven't got their sub part of the fab going for that at the moment. Right. That's some. Let's just go back here. I think Intel process technology. I think the only thing to say about this is, and I'm not sure I put a slide in, so I'll make it as a statement and then we'll skip over the slide of that. Typical high-end stuff, there are 1,000 processes to make a single transistor, a single die. So you etch, you coat, you then you lay down, you then 1,000 times. There are 1,000 parts of the processes. Actually, some of the processes are the design processes as well, but they have to go through very strict checking processes to get them in, which they're very good at. But 1,000, just bear in mind, it's in fact. So here's now for 6G, then we need a new process. Basically, that's what the message is. The 4,500 key IPs, that means patents, intellectual property things, from 50 global intellectual property partners. So that's the kind of integration that you've got. Okay, let's move on. This is the 1.77 times logic density, less logic power, which is needed for the ICs on that. Excuse me a minute. So, right, this is again gives you some idea of the mixing of the chips. This is really system in a package. The Apple iPhone series That's a fairly early one, which was there, and things stitched together with wires going from one chip to another, etc. Mainly the RF kind of stuff. Again, there are different technologies. This was this sort of a build-up of layers, which there's a lot more layers in the latest systems on here, and this is typical BGA, which is ball grid array, which you can see on there. So the techniques have got really wonderful. Now, if you want to know the latest techniques, I'm going to give a little bit of plug for this YouTube channel, Anastasia in Tech. And when I got to do Ian's notes and trying to find out what he was going to say, I suddenly realized that actually 2 or 3 years ago he'd said to me he got his stuff from Anastasia in Tech, who's been running this YouTube channel. And it actually tells you she is a hardware engineer, or was a hardware engineer, and she gives a very good description of the latest technology on things. You know, the new silicon, the secret behind Apple's new silicon in the phone, etc. Breakthrough in a very easy to listen to or watch way. So I'm keeping an eye on that, and if I have to give this lecture again, I'll update using her example. Now I'm going to rattle through fairly fast now because I think we've covered a lot, but just to give you a flavour of well, this is actually the RF side, the radio frequency side, and the millimeter wave transceiver block which we've got at the moment, needed for 5G radio. And let's pick out something from here. This is actually a paper which was actually to do with the modems and Vitobi decoders on that, which is going on. And here is now the latest, or reasonably latest, package. You see it's just getting, this focuses a bit more on the radio frequency side rather than the digital side. So this is showing all the radio frequency and the antennas on here, different antennas on there. And you can have several antennas on a mobile phone. Certainly on them, you'll have at least 7 to 9 antennas on a laptop like this. Chipset Qualcomm, keep moving on, gives you some idea of the complexity you've got. Pictures again, Qualcomm transceiver, gigabit LTE, 4x4 MIMO, which is said, that's to do with the channels to antennas. So that is 4 channels transmitting in different, at the same time in different directions, if it can be, and 4 channels receiving. So you can really optimize which part of the channel is actually, which antenna or little mini antenna which is actually receiving the best signal, and you combine them and so on, multiple input, multiple output. Another transceiver, and you can see some nice inductors on there. 4 nanometer chip, again giving you some idea of what's going on, and that's again showing this is a little bit more digital on that, showing the CPU cluster, etc. Snapdragon, 5G, etc. This is the kind of things you have to do at the moment. That Any Questions was actually a brilliant idea which Ian had, and I wish I'd done that. He took his notes at the time of COVID, and we were all lecturing on Zoom, and I like to look at you guys and actually see, okay, I haven't given you time to ask me questions yet, but if I'm doing a class, then I'll take questions on the fly, because I've got 1.5 hours rather than the less than 1 hour, which I'm supposed to take this time. So anyway, I like to look and take questions, and I'll take them at the end, if you don't mind. I saw you. Right, okay. So, but that was a brilliant idea, because there's nothing more dispiriting than actually zooming with a list of names on one side, no faces, and you can't see any reaction because everybody switches off. Well, if you've got a big class, you can't hold, but you can have the list of names on that. So anyway, that's a good idea. So he used to stop and take questions like that. So we're now into the RF technology a little bit more, the kind of things we do. This is up converting transmitter and what has to be done. The thing is that you start at a low intermediate frequency and mix it up to the RF frequency, the high frequency, by a local oscillator, excuse me. Mixer techniques, going to skip over that, but there are some very clever techniques which are in here. Spectrum shaping needed, baseband, etc. and clever ways of doing it. This is an interesting one. This gives you a clue of the modulation type. Quaternary, 16 quaternary amplitude constellation modulation, or where you have amplitude in one direction and phase in the other direction, and that's the system which is used for your digital TVs. It's used also in the mobile phones. Direct conversion. This is, I'll just stop for this one. This is a very interesting thing. This is a Gilbert cell mixer. It's a wonderful device. It's used analog, it's used digital, it's used for all sorts of things. It's a very clever thing. It's actually two what are called long tail pairs, and that is combined in that way. And it's a very, very versatile device. The really neat thing about it, and particularly done in high RF, there are no capacitors here, none at all. And in fact, you can make arrays of these things with no capacitors. So you can actually get rid of one of the big problems. And I'm going to, at that question, skip on to skip through this and show you what I mean in a moment. These are the receive side. I'm going to skip on various tricks and that you can actually direct conversion. Software-defined receivers use all these tricks. They're now getting into the mobile phones. So keep moving on. Direct conversion receives lots of architectures which you can have. And this is where I'll quickly move on to some of the simpler technology. Dielectric combine, compact size, etc. These are filters. Those are the actual, they're just lumps of suitable piezoelectric, usually, certainly dielectric resonators, and these can all be coupled. They're all little miniature array, and they're all inside your mobile phone. F-bar structures, this is a more complicated version, and the piezoelectric layer, is to convert basically the electrical signal into a sound signal. These things work on sound vibrations, resonant sounds. They are a direct conversion. You can make ladder filters on that. Right, moving on quickly. Power amplifiers, there are various arrangements. This is where you start to need to switch the power output to, for example, different aerials or different parts of the system. And so you need a switch. I'll just show you what we need to do about that in a moment. So this gives you, this is a fairly early one where you've only got two antennas and you can switch from one to another with all this clever switching done here. This is a different aspect. It's much easier when you've got this 16 by 60 or 16 QAM signal to actually get it to the output in two ways. You take you clip it and make it a constant amplitude signal which retains all the phase information or frequency and phase information, but it does not retain the amplitude information. So you take the amplitude information off and then you feed it to combine it, to put it back in by modulating the amplitude of the PA. And if you do that, it's very much more efficient. You know, it's up in the sort of it can be up in the 80-90% efficiency on that. Switches, this is all technology. This is the kind of switch which you would have in RF, and this is a monolithic switch, single pole, 7-throw switch. So it's got 7 outputs, single pole on that, or nothing particularly on that. But that is, I was going to say nothing mechanical about it. Well, there is something mechanical about it. It's what's called MEMS, microelectronic mechanical systems, or microelectronic systems that combine mechanical and electrical components and are fabricated using semiconductor fabrication techniques. So these can go onto some place on the silicon itself in that way, and they can use the switches. And here's some pictures of the rough idea RF MEMS switches, metal contacts and capacitor designs. They're basically controlled by a voltage. The relays, they're essentially tiny relays, but they're not controlled by current as the normal relay switches are, but they're controlled by voltage. 5G, EXA, mobile internet traffic growth. This is why you need it. EXA is 10 to the 18. This is the amount of data per month through the mobile network system. And look at the numbers. It's huge. And look at the growth. It's 2017. It's growing. It's going up. So that gives you some idea of what digital needs are for the system. Here is a little bit of here's the billions of devices. So this gives you some idea of the billions of devices. That was up till 2023, and there's the various things on there. I won't go through it, but it gives you a general feel on that. So various things are needed for 5G. They're listed here, and you can quickly read and ask me questions about it later. But how can you start meeting some aspects of this? This is actually a plug which Ian Robertson did for the University of Surrey 5G Innovation Centre, New World Centre at the University of Surrey, 5th generation technology which will revolutionise and internet access in the UK has been given a go-ahead. So for that was back in 2012. It's been working for 10 years now. Right, Samsung claims that this is actually University of Surrey working for Samsung. Okay, gives you some idea. This is what you have to do to get up to the higher band of 28 gigahertz, which I mentioned, the millimeter wave band, that is. And look, it hasn't got one simple antenna, it's got 64 antenna elements, which you can do, obviously, because the wavelength is so much shorter. Higher data rates. Well, here's the problem, part of the problem. How much spectrum have you got? Here's the spectrum allocation, frequency allocations. Obviously won't go through it. I'll just tell you it's pretty dense. But here's another aspect of the same problem. Some frequencies are better than others, so to speak, because there's a propagation loss versus frequency, which is fundamentally because of the atmosphere and whether it's raining or not, or whether it's foggy or whatever. And it's different at sea level and at 9,000 meters altitude. But there are certain characteristic features of this at round about 20-25 gigahertz, there's a high absorption because of water vapor. At 60-70, there's a high absorption because of the oxygen in the atmosphere. Now this is the band which is used for car radars, because it actually means that you can get a short distance very well, but it cuts off very rapidly. The attenuation drops off a bit like a stone. There are other ones, so we're moving up into this is the sub-terahertz band, so there's still problems. So you have to choose the right places for where you operate it. But you can see, and this is the oxygen is fairly constant. The water is certainly not, because the humidity is very variable. Fortunately, the oxygen level doesn't vary very much, otherwise we'd all be in problem. So, right, the problem is, at these higher frequencies, to get more power out. So you have to, you can power performance solid state sources and so on. You can see that actually the blue curve tells you the best you know it can be done with certain technologies. But anyway, that is the problem, the challenge of higher data rates. In a nutshell, if you want higher data rates, you go to higher frequencies, but the price you pay, that you can only achieve lower transmit power, so it's a trade-off. Higher data rates, one of the things is steerable antennas, and here is a 70-80 gigahertz line of sight link for 1.25 gigabits Ethernet, so that's extending your internet, if you like, for rural areas. And here is the kind of things you have, various antennas on you don't have a single you have a beamforming network, and you have this kind of arrangement. You don't have that, you have this. You can actually switch the beam reactively to pick up or send to a particular sector of the mobile. Right, that's a 60 gigahertz wireless. So if I wanted to put this computer over there and not have a cable going to the HDMI, I could use one of these things, and it's quite cheap now, so you can have wireless HDMI cables. Moving on, picking out one or two things. Here's a cylindrical antenna array. There's you can vary the elevation, you can vary the azimuth on that. It's a massive multiple input, multiple output arrangement, essentially. Here is some Doherty amplifiers down there, Broadcom TX, you can, with all the various bits identified on there. Here's an interesting one. I was talking about to Norman earlier. The 5G needs multiple antennas inside the handset to do really well, so that is acting like a base station with antennas, and you will have a little phased array on the sides and on the top capable of doing that kind of thing in the next generation, and just before we get to 6G. That's the kind of thing that is being looked at. This is the antenna array. It's no trivial job to actually to make the feeds for that. Moving on, Internet of Things, pervasive computing, all these kind of things for 5G, and wearables, body area networks, new forms, 5G, augmented virtual reality, etc. The thing about 5G, and particularly 6G, the most important thing is that it's very or much lower latency. so that if you're a surgeon and you want to do an operation on somebody on the other side of the world, then you need 5G networks at least 5G and preferably 6G networks at both ends to be able to control the robotics with a suitably low delay. So that's what part of hidden away in the 5G and 6G. That is what the goals are. Here again is the 5G, 6G Innovation Centre. They've changed the name because it's all 6G now. But remember, 6G is at the moment only doing research and setting the standards for the next generation. It won't come for probably another 5 years, insensibly. And the infrastructure for it, maybe the most important thing is if we get a lot of self-driving cars to keep them under control, you'll need a very big infrastructure of the network for that. So this is a book which describes some of the book. The EPSRC and DST, that's academia, and that's essentially Ministry of Defence, have joined together. They've got various projects which they have on their Titan hub on all spectrum, HASC, etc., etc., etc. So all these projects are going on in the background, and this is one of these multiple beam jobs, and University of Glasgow published a breakthrough 12th of April 24, so earlier this year, that they're advertising their wares as much as they can. Transceivers and mobile devices summary. So this is now the end. So I'll quickly just pick up on those. High technology products with a continual push so lower cost is a continual push. Prices are shocking for individual components are shockingly low. I haven't got an example. Ian would have been able to give some examples, but they really are very, very low. Close integrations of digital signal processing and RF is essential. I have sort of stressed that already, that you've got to get them both into the same handset. Multi-band transceivers, multiple antennas. Yes, all this going up to 6Gs is you'll be operating on 3, 4, 5 possibly bands capability, or switching from one to another depending on what you're trying to do. 5G is key to the Internet of Things, robotics, virtual reality. Bandwidth and latency is much lower. 6G research already forging ahead, including sub-terahertz link, but it is still rather immature. And this is the end. Ian, on his last slide, advertised, and so he should, his two books. I've got this one. Although it's actually 2016, it actually contained description of all the slides, or most of the slides that he put in, except for the ones he'd got from Anastasia on tech. So that was it. And okay, any questions?
I don't know about you, but I'm suffering from brain overload. Thank you, Mike, for that whistle-stop tour through 1G to 6G. You said there was one question early on, or someone had a question. Can we, yes?
What are some of the challenges stopping transistors from getting smaller?
I'm sorry, I'm hard of hearing. Can you relay?
Some of the challenges that are stopping transistors getting smaller.
Basically, when you go below 2 or the spacing between atoms is somewhere between, is round about the nanometer level. That's the problem. Okay, you can get things closer together. You can actually get the use a sort of line of atoms or piece of atoms and another line of atoms, and they average out and you can get them closer together. But it really is that physical spacing of what is called the gate area in the transistor. That is the physical limit on that. If you're talking about power, then there are some tricks which you can do, which is a thing called LDMOS, laterally diffused MOS, metal oxide silicon substrate. But that's a very clever thing, but only for power. A better name for it, which they won't use, which I try and promote, is long drain, because the drain inside the transistor is a much longer length, and it enables you to operate at the same current but a much higher voltage. So it's a very clever technique. But basically, we are at the limits now. We really are. The physics is the limit.
Yes.
I've been living in the same house for about 25 years, and we've had antennae about 400 metres as the crow flies away from us, so they're quite high. We've gone through 3G, 4G, 5G. Now, you were talking about steerable antenna. Has that come with just 5G? Because in all of that time, my signal strength has been rubbish. So
where do you live?
Technology has not changed.
Where do you live?
In Maidenbower near Crawley.
In
Maidenbower near Crawley.
Oh, okay.
Yeah, there's three of them.
It's useless, is it? Yes.
Yeah, there's a couple of extra providers over the years.
Have you got a 5G phone? Do you get 5G ever in that area?
I get 5G, but where I live, I guess I'm just in the shadow. But I thought now with steerable antenna, or I mean, they must have changed the antenna to give us the 5G.
Yes.
Presumably did that.
The way in which 5G is going to work is putting a base station on every lamppost. You know, enormous infrastructure costs. And I was discussing, I think it was with Norman, if I've got 5G phone, that's a 5G phone, but the number of times it's actually using 5G is pretty low. And the kind of situation, I like to watch cricket after I go with one of my sons, and if we're at the Oval or at Lord's, or even actually down here in Worthing, the cricket ground, the Sussex cricket ground, then everybody's doing what I'm doing, is getting a commentary off the phone. It'd be nice if you could actually watch the playback that is going out. Now, if everybody tried to do that, you know, sort of thousands, you know, over 1,000 people on phones, you need 6G. You won't do it on 5G. The network overloads.
So the G description is the data, but hasn't the transmission signal improved as well over that time in the aerials? Surely they've changed the aerials as you've gone through the...
I mean, the 6 is just because it's the next things. The real thing about it is a much greater data bandwidth. That's really what it is, and lower latency. That means it takes less delay to do all the signal processing and all the rest of it. So I mean, the more aerials, more antennas that you need for 6G is simply because the wavelength is so small. You know, you're in millimeter wave territory, so the half-wave dipole is pretty small. So you have to use different techniques on that, and they go down in transmission efficiency. So you've got to fill in the area to the same size as a lower frequency band, you know, 10 centimeter or whatever it is. So you go down to a millimeter. You've got to fill in with a lot more aerials to get the same path efficiency for a given power.
regards to the progression of 1G to 6G and above, do you think we'll ever reach a saturation point?
In the progression from 1G to 6G and perhaps onwards, will we ever reach a saturation point?
Oh, good question. Yes. Possibly yes. But I say that very carefully because look at Moore's law. That has gone on about 5 times longer in years than it was ever predicted to do. So, but goodness knows, if you go beyond that, go well into the terahertz region, that'll be the next thing, and then you'll be in trouble. You will be basically nudging up into the optical region, and you'll have to have certainly infrared. That's safe. Optical aren't safe for lasers, and that you'll have to have a very different system. Okay.
Do you know what the best method is for determining what base stations?
But if you look back at the progression, the first thing which is done is to create the standards for the system, and they're always 5 years behind the time. They're always. So, in fact, they do a good job. So 5 years. That's my guess.
Any other questions from anyone? Oh yes, yes.
May I ask another one?
Certainly.
So because these frequencies are getting higher and higher, and obviously the wavelengths are getting shorter and shorter, we start running into more and more issues with signal penetration, especially through the old thick buildings that UK has. Like, what are some of the ways that you can circumvent that issue in terms of going to 6G and say even beyond 7 and 8G?
Okay.
As the frequencies are going higher, we're going to have more problems in terms of sort of penetration into buildings.
Most certainly, yes.
Obviously,
And how are we going to
Most certainly, yes. I mean, that railway station, Euston or whatever, was a perfect example of that. Now it's a little bit selective because there are certain run about the old TV bands, for example. Then certain brick walls had a lot of absorption, and actually if you went higher in frequencies you got less. I mean, I live in an old house with thick walls, and my internet, I have to have repeaters in different parts of the house, you know, because because of the thick walls. It is a big problem, and I've actually been at a conference some years ago where a university was saying how big a hole should. So if you've got that problem in a house, and you were prepared to make a hole in the wall, and then put something like plasterboard or something low absorption over it, how big did it have to be at the various mobile bands? And they'd actually done it, and it was quite big. I wouldn't want it. Okay, if you've got a serving hatch from your kitchen to your dining room, then you could make sure that your internet system is up against the serving hatch or in the serving hatch. Okay.
So basically, big holes in your houses. That's not what you're proposing.
So basically build big holes into your house.
Yeah. I'm not prepared to do that. Actually, I've got thick wooden doors in part of the old part of the house. I leave them open sometimes. Get better signal from the internet, that is. That's okay, it's not mobile, but it's the same sort of thing.
Okay, thank you. Oh yes, Norman has that.
So, what's driving the need for 6G? I think I'm not sort of understanding that correctly.
What's driving?
What's driving the desire to go to 6G? I'm just trying to... is it a military thing?
It's not just military. Some people say it's automatically driven cars.
IoTs probably.
Somebody else said something?
Internet of Things, robotics.
Sorry, I didn't hear.
Robotics.
Yes, yes, thank you very much. That is to Ramon. Robotics is actually probably the most important thing, because you need, under certain conditions, you need very low latency, very short time delay, quick reaction on that. Certainly for medical robotics, where you're doing operations with robots, then it's absolutely crucial to, you have a glove which sort of reacts back and forth to the scalpel, which is actually in the hand of the robot itself, that kind of thing. That robotics, medical robotics, is absolutely crucial. You may be able to do cataract operations remotely on the other side of the world, things like that.
Okay. Well, I knew they were complicated, but perhaps not quite that complicated. Mike, thank you very much for leading us through that. I think I need to take a course in...
Come on the Surrey course.
So, perhaps, I hope you now understand a little bit more about the transition from 1G to 6G, and would join me in thanking Mike for giving us this presentation this evening. Thank you, everyone.